Constant velocity, Richard Morin. The lab instructions were to observe the motion of a ball at constant speed, videoing the motion. This motion was then to be analyzed both with tracker and computational coding. I conducted this experiment using a volleyball as my rolling object. The purpose of this lab was to evaluate an object moving at constant velocity both experimentally through observation and computationally through coding. Overall, this relates to a larger purpose of understanding the physics principles behind the concept of constant velocity. Through this lab, it was evaluated that an object moving with constant velocity will experience a positive linear position versus time graph. Additionally, an object moving with constant velocity should experience equal distances traveled per time step. So the models and principles used in this lab were primarily Newton's second law. This is the law of inertia, stating that an object in motion will remain in motion unless acted upon by an external force, and is also represented by the equation force equals mass times acceleration. Newton's second law is applicable in this experiment since there should be no external forces acting upon the moving ball. Since constant velocity is being experienced, the ball should remain in a state of constant velocity due to the model of inertia. Additionally, due to the equation force equals mass times acceleration, there is no force being experienced, so there is hence no acceleration, indicating a constant velocity. The system in this lab was a rolling volleyball, and the ground, the track that the ball was rolling on. The surroundings was everything else in the frame of the video besides the ball, including objects such as the wall behind the ball. The initial conditions of this lab were that the ball starts at an initial speed of 0, and is then propelled with a push to which it remains at a constant velocity. Additionally, there are no external forces acting upon the ball besides the initial push being the push that generates the initial velocity. Here's my video. In this experiment, I tracked the position of the ball frame by frame using the online tracker, to which I created this position time graph scene. As seen, there's a positive, roughly linear correlation between the position and time of the ball. During the computational aspect of this lab, I created a code with the following parameters in order to simulate constant velocity. The initial velocity was 0.23853 meters per second, which was found by dividing the first position point by the first time point in the experiment. The initial ball position was a zero vector, and the delta t was 0.03 repeating, which was the length of a frame in the experiment. Additionally, the ball position then changed 0.07951 meters with every time step, as this was the first change of position seen in the experiment. The following linear positive graph was generated. When both the experimental and coding data were put onto one graph, the following graph was observed. The similarities in the data is that there is a linear correlation between time and position of the volleyball in both the experimental and computational graphs. Additionally, the initial starting velocity is the same for both datasets. However, there is many differences in the data between the coding and experimental labs. The computational model final position was greater than that of the experiment. And additionally, the slope of the computational model graph was perfectly linear, while the slope of the experimental graph has slight fluctuations and a general decrease in slope. Potential errors in this experiment was that the ball may have bounced during movement, indicating non-perfect constant velocity movement. Additionally, there may have been inconsistent plotting of the point mass in the tracker program, and that the existence of friction in the experiment and the lack of such a force in the computational model. All combined, these three potential errors could have altered the position graph as seen in the experiment. According to this what-if question, all results seen would be the same. However, they would now be in the direction of the new axes. The magnitude of the velocity will not change, meaning that the change of position will be the same, albeit in a new direction, negative x versus positive x. And according to this what does it mean question, in order to achieve a net zero force, there must be equal and opposite forces acting upon the moving volleyball. In this scenario, there's an initial push which gives the ball its velocity and a frictional force acting against the ball. Hence, it can be considered that these two forces cancel out in order to reach a net zero. In conclusion, the position versus time graphs for constant velocity were evaluated both under experimental and computational conditions, determining that they both experienced a positive, roughly linear correlation between time and position. Additionally, the computational model had a perfect slope, while the experimental model had a non-perfect slope, indicating that the constant velocity is difficult to perfectly obtain under real-world conditions. Thank you.